So, I am going to be showing another demo that computes the value of TTR. Again, I am going to be using NLTK platform to perform this operation. So, in this case, we are going to be taking two corpus. One is Brian Story's corpus, the second one is Austin Emma corpus. We want to find out the lexical variety of both Brian Stories and the Austin Emma text. As in the previous case, I am getting the words. I have two different word set now. One is for Bryant, other one is for Emma. I am also using the stop words to remove all the stop words from the word collection. Okay. So, as in the previous case, I am converting all the words into small letters and making a collection for both Emma as well as for Brian. And then I remove the stop words for both Emma and Brian. Okay. So, now what I am going to do is I am going to find the TTR ratio for Bryant and Emma. So, in this case the length of both Austin Emma text and Bryant Stories text vary. Okay. So, we cannot be comparing for two different word lengths. So, I am going to be using the count up to 15,000. For example, for every 15,000 words, let us find out what the TTR ratio is. Ideally, how is it done is it is done for every 1000 words. You take 1000 words of Bryant, 1000 words of Austin Emma corpus, and then perform the TTR on both, and then see what is the lexical variety in both these texts. So, in this case, for the sake of this demo, I have taken 15,000 words. Okay. I have taken the first 15,000 words and then trying to find out what is the TTR value for both Bryant corpus and Emma corpus. Okay. So, when I perform the operation, you can see that the unique vocabulary is represented by the set here. Okay. So, when you use the operation set, it automatically removes all the duplicate words and then keeps only the unique set as the vocabulary, and then you get the total number of word count in the given corpus. Okay. When you do the operation, what you have in the next slide is a table that represents the vocabulary and the type token ratio for each of the corpus. As I mentioned earlier, it is not reasonable to do or compare two unequal sized document. That is why I have restricted the token count to 15,000 in these cases. So, if you look at the vocabulary, since this is the same, we have the vocabulary count of 2,796 and 3,274 for Jane. And then if you look at the type token ratio for Brian Stories, it is 0.19, and if you look at this, it is 0.22. It is almost close, but Jane Austen has used more vocabulary than Brian Stories. So, this is used to compare two different English literature text and find out who had used better vocabulary in a sense in terms of the number of vocabulary used. Okay. All right. So, what is the application of this? So, as I mentioned earlier, it is used to monitor the vocabulary usage. You can monitor the child's vocabulary development. You can also estimate the vocabulary variation in a given text. Continuing on the discussion on the important terms in natural language processing, now we will take up inverse document frequency. Earlier we spoke about the term frequency, where we try to count the number of occurrences of a given term in a given document. So, counting the terms does not really give you the sense of what really is present in a given document. So, we would like to extend that little further in terms of adding the new technique to find out the relevance of a given document. So, in this case, we are going to be finding the inverse document frequency across the corpus. So, let us first define what inverse document frequency is and then move on to the examples and how it can be utilized to find the ranks of the documents in the corpus for a given word and so on. Okay. We also need to attenuate the frequency of terms that are occurring very frequently. So, if you have too many of such terms, they are going to be curtailing the relevance of the other terms in the given document. So, we want to really make sure that there is some kind of a normalization across the corpus done, so that the retrieval of documents for a given term is always in the normalized fashion. Let us first define what IDF is. IDF is defined as the log of the ratio of the number of documents in a collection to the document frequency. Let us first define each one of those. N is the total number of documents in the collection, and the DFT is the document frequency. That means it is the count of the documents containing the given term T. So, that means IDFT is for every term in the given document. By doing the IDF, rare terms gets a significantly higher value. For example, there are 1000 documents and then a particular term occurs only once in the entire corpus. That means the IDF value is higher, and if you have a term appearing in every document, then the IDF value for that particular term is lower. So, in doing so, we are actually attenuating the commonly occurring terms. It also now brings into the concept of informativeness in the document. What I mean by that is, even if there are terms that are not really appearing in all the documents, we still have some relevance to those particular terms in the given corpus. It actually reduces the TF weight of a term by the factor that grows with the collection frequency. Suppose if you have a term with a larger frequency, and if it appeared in all the documents across the corpus, the TF IDF, if you multiply both, you will have a normalized small value. So, otherwise if you only consider the TF, the value of the TFT would be very high. Okay. So, by extending this to the terms where that particular term appeared in every document in that collection, then IDF would be 0. That means the term is not very important to the retrieval operation. Okay. So, as I mentioned earlier, we have to combine the TF and IDF. That is the ideal situation in many corpus. We will do the TF and IDF composition to find the value of a term. So, this is very commonly used in information retrieval. So, in this case, the value of a term is very high if it occurs within a few set, or occurs within a small set of documents. The value is very low when the term appears in all documents. So, that means TF IDF is a very standardized term or the technique that we want to use in the corpus collection. Okay. Let us take one small example and then explain the importance of TF IDF. So, just explaining rather expanding the definition with the sentence there. IDF of a term T equal to log 10, I am taking the base as 10 here, total number of documents in a corpus to the count of documents with the term T. So, IDF is now the measure of the informativeness, as I mentioned earlier. So, if we consider a corpus with 1000 terms and we assume that there is a word moon that occurs in some document, let us say in 100 documents with the following frequency. So, in document 1 it appears about 20 times, and in document 1000 it appears about 20 times, and then The rest of the numbers, if you add up all those frequencies, it may not be 100 in this case, but the rest of them probably would be appearing in other documents as well in small numbers. So, if you calculate the IDF for the term moon here, it will be a logarithmic value of 100,000 by 100, that means it is equal to 3. And then the term frequency and IDF would be equal to 0.141. If you do not consider the TF IDF and only consider TF, the word Andromeda, if it appears only once in the entire corpus, it will have no relevance at all, because if you assume that it appears only once in one document, let us say D1, then it is going to be 1 by 427. So, it is of very less significance, but when you consider the IDF for this, it would be equal to 5, right. The IDF is going to be 5 and then the TF IDF is going to be 0.0117, it is here. So, if the word the appeared in every document, then the TF IDF will be equal to 0. That means, the entire word the will not be considered at all in the relevancy of documents. Okay. So, now let us find out for the given word moon, what are the ranks or the rank order of all the documents depending on the TF IDF. So, this is one of the applications of TF IDF using which you can find the ranks of the documents based on the word moon here, right. So, what we are seeing in the table here is the TF IDF for the word moon for document 1, 2, 3, 9 and 1000. So, if you consider these 5 documents, the ranking would be like this. The one with the highest ranking will be termed as rank 1. So, if you look at that, the ranking would be ordered with respect to the TF IDF in the descending order. So, when you display the results, you start displaying this as the first document, this as the second document, third, fourth and fifth and so on. Okay. So, using TF IDF, it should be possible for you to rank the document for a given word, and this rank is going to change if you change the word to something else. Okay. So, let us look at another empirical law in the natural language processing, which is called as Zipf's law. Zipf's law states that for a given corpus, the frequency of any word is inversely proportional to its rank in the term frequency table. That means, if you have a word with a very high frequency and the rank would be equal to 1, right. And then if you take the second one in that rank, the frequency and the rank, if you multiply, should be same as what you get for the first frequency and its rank. So, that means, if you have this could mean that the frequency of a given term and its ranks, if you multiply, it should give a constant. So, this should be same for all the terms in the given document. So, if here we consider alpha to be equal to 1 and R is the frequency rank of the word and FR is the frequency of the term in the corpus. Okay. The most frequent word will have the value 1, that is its rank, and then if you look at the second one, it will be represented as the frequency of that particular word would be equal to 1 by 2 to the power alpha, and then third would be equal to 1 by 3 to the power alpha and so on. So, if you multiply the frequency and the rank, you are going to be getting a constant value. This is what Zipf's law is really stating. Is it really true in the case? This is just an empirical law. It may not work out very well for every document that we find or the corpus that we find. So, it roughly gives you that the frequency and the rank would be almost equal to a constant value. Okay. So, this is useful in terms of modeling the corpus. Okay. Let us look at a small demo which really computes the Zipf's value with respect to frequency and the rank, and then see how it shows the table as. So, I am not going to be talking about all this. You probably should be able to find some details about that in the internet. So, I am going to be taking only the very important one that we have here. Okay. After collecting all the terms from the corpus, we are going to be finding the frequency for every word. Okay. The frequency for every word is counted using this, and then the ranks are found using the second one, right. And then for every word that we have found, we are going to be listing by the rank, its frequency, and the rank and frequency, and then finally we print that particular table. So, if you do this operation, you are getting some table where the words are listed as the first column, the frequency is listed in the second, and the rank in the third, and then frequency and the rank in the fourth one. If you look at the frequencies with a high rank, right, you do not see any correlation to what Zipf's law is stating. And then if you go to the ranks at the lower order, okay, you see some correlation there. Okay. That means the commonly occurring terms in the mid frequency cycle, you have some kind of a correlation that comes. So, again I am stating that this is only used for modeling the corpus and not exactly the representation of any of the corpus. Okay. So, moving on to the next empirical definition, Mandelbrot approximation again is an extension of the Zipf's law, where Mandelbrot studied lot of corpuses and found that there could be some approximation, so that the frequency and the rank multiplication should yield to some standardized result, rather than some kind of an infrequent measurement that we have obtained in the earlier cases. So, he tried to modify the same Zipf's law by adding a beta. Okay. So, if you look at that, there is only one addition to this, which is beta. So, if I make beta to be equal to 0, then it is same as the Zipf's law. So, if you look at these approximations or the empirical formula, you will wonder that how the entire corpus could be fitted into some kind of an empirical relationships of this type, even though they are not very accurate in nature. Okay. So far we have seen the kind of operation that we can perform on a document, perform on the corpus, and then how we can combine the document frequency with the inverse document frequency to find the ranks of documents for a given word, and so on and so forth, right. So, there is one more which you may want to look at, which is the Heap's law. So, I am not going to be spending a lot of time on this, but this is again an interesting law which states that the number of unique terms is proportional to the total number of terms found in the given document. That means, according to this law, the dictionary or the vocabulary size increases linearly with the total number of tokens in a given corpus. So, this particular law really emphasizes the importance of the compression of the dictionary. That means, if you have a vocabulary captured with respect to run, ran, running and so on, it is going to really increase the number of terms, and every word would be considered as a term which is not really right, correct. So, if you want to really compress the size of the vocabulary only with respect to the root of the word and not with any other additions to that. So, this particular law really emphasizes that by reducing those words or doing some operations on of stemming and lemmatization, you should be able to reduce the size of the vocabulary, and thereby the representation in the memory would be very minimal and so on. Okay. So, with that, I conclude the session with respect to what you can do with the documents, in terms of converting them into statistical numbers and so on and so forth. So, I am going to be giving you 2 exercises that you want to try, and then make sure that you understand the definitions and what is really happening in all these empirical laws and so on. So, this is going to be about one is for the Zipf, and other one is for the Mandelbrot. So, what you have to do is you have to write a program to find out whether Mandelbrot's approximation really provides a better fit than Zipf's empirical law. So, for that you may want to use the same corpus for both Zipf and Mandelbrot. And then the second one would be to write a program for Heap's law and find out the prediction of vocabulary in any corpus. Also find out whether it is very closer to the actual size of the vocabulary of the corpus. Okay, so how do you do that? This actually the second one consists of 2 parts. One, you have to write a program for the Heap's law and then estimate the vocabulary that you get, and second one is you have to actually use either NLTK or any other platform and then find all the words and then remove the duplicates and then only get the words in some list and then make a count of that and find out whether that count is same as what Heap's law is predicting. Okay. This slide shows the references that I have used for this lecture.